Electrical Measurements and Instrumentation, Lecture 6. In this video, we are going to discuss about moving coil type of instrument. In that, we will discuss permanent magnet moving coil type of instrument, which is also called as PMMC instrument. And this instrument is most commonly used as deflection type of instrument. Permanent magnet moving coil is the basic measuring instrument which can be used for measuring current and voltages. They can be converted into either voltmeter and ammeters. This is the simple structure of permanent magnet moving coil. Here we have two permanent magnets which is having north pole and south pole. In between a moving coil. This is the coil, and which is core, aluminum core, cylindrical core we are using it. And this is your spindle. Spring is connected either sides of this moving coil, and the pointer is connected to the spindle, and there is a scale here. This is the top view. So this is north pole, this is south pole. A radial magnetic field is produced here, and which is aluminum cylinder. These two are moving coil, and this point is connected to this spindle. This permanent magnet moving instrument is the most accurate type of DC measurements. Permanent magnet moving coil type of instrument is exclusively useful for measurement of DC current or voltage. If you look at here, the name itself indicates that the magnet what we are having here, they are permanent magnets, and the coil is moving. That's we called as permanent magnet moving coil. If you want to measure a current at a particular line, we connected these two terminals at there wherever it is required, and the current is flowing through this coil. When the current carrying coil is placed in a magnetic field, it experiences a force. The law is called as Lorentz force principle. So PMMC instrument operation is similar to DC motor principle. Let's see the construction point of view for this PMMC type of instrument. If you look at here, a permanent magnet with two soft iron pole shoes. This is the permanent magnet, two soft iron pole shoes. The second one is a cylindrical soft iron core is positioned between the shoes. This is this brown color is cylindrical soft iron which is placed in between these two permanent magnet soft iron pole shoes. And the moving coil is wound with many turns of enameled or silk covered copper wire. This coil is mounted on rectangular aluminum former which is pivoted on jeweled bearings. The coil moves freely in the field of permanent magnets. Most voltmeter coils are wound on metal frames to provide the required electromagnetic damping, and most ammeter coils, however, are wound on non-magnetic formers because coil turns are effectively shorted by the ammeter shunt. The coil itself therefore provides electromagnetic damping. So the damping here it is electromagnetic damping. The damping torque is produced in PMMC is electromagnetic damping. Coming to this moving coil, let's see what are the things in the moving coil. The coil is the current carrying part of the instruments which is freely moved between the stationary field of the permanent magnets. The current passes through the coil, deflects it, due to which the magnitude of the current or voltage is determined. The coil is mounted on a rectangular former which is made up of aluminum. The former increases the radial and uniform magnetic field between the air gap of the poles. And the coil is wound with the silk cover copper wire between the poles of the magnet. So these are the things in moving coil. Coming to the magnetic system, old style magnet system consisted of relatively long U-shaped permanent magnets having soft iron pole pieces. The PMMC instrument using the permanent magnets for creating the stationary magnets. The Alcomax Alinco material are used for creating the permanent magnets because this magnet has the high corrosive force. Corrosive force means the corrosive force changes the magnetism property of the material. Also the magnet have high field intensities. The flux density used in PMMC instrument vary from 0.1 Weber per meter to 1 Weber per meter. So these are the specifications of the permanent magnets. Coming to the deflecting coil, which is in rectangular in shape, wound on aluminum former with large number of turns. Width of the rectangle is less than the distance between poles of the permanent magnets with an air gap. Coming to the aluminum core, a light aluminum cylinder with pivoted on top and bottom is made to fit over the axle of moving coil and acts as damping mechanism. This moving coil and permanent magnets produces deflecting torque. Now coming to the controlling torque. So here in PMMC type, the controlling torque is produced with the help of spring. Spring control method is used in this type of instrument. So one of the two controlling spiral springs is shown here. One end of the spring is fastened to the pivoted coil and the other end is connected to an adjustable zero position control. On the top of the instrument we have zero position adjustment control. So that end is connected to one end of the spring. Coming to this control, in PMMC instrument, the controlling torque is because of the springs. The springs are made up of phosphorus bronze and placed between two jewel bearings. The springs also provide the path to the lead current to flow in and out of the moving coil. The controlling torque is mainly because of the suspension of the ribbons. And the current in the coil must flow in one direction to cause the pointer to move from the zero position over the scale. If you change the terminals, automatically the pointer will deflect in the opposite direction. So that's why the current in the coil must flow in one direction to cause the pointer to move from the zero position over the scale. The terminals positive and negative indicates the correct polarity for connection and the instrument is said to be polarized. And it cannot be used directly to measure alternating currents without rectifiers. It is purely a DC instrument. PMMC instrument is purely a DC instrument. Coming to the scale, the mirror is placed below the pointer to get the accurate reading by removing the parallel axis error. Parallel axis error means the shadow and this needle try to make it, the shadow is shown in a mirror and this pointer must be in parallel. Then only you can measure the reading without parallel axis error. Coming to the pointer and scale. The pointer is carried by the spindle and moves over a graduated scale. The pointer is of lightweight constructed and apart from those used in some inexpensive instruments has the section over the square twisted to form a fine blade. This helps to reduce parallel axis error in the reading of the scale. Then the coil is supported between two jewel bearings and two prosperous bronze hair springs provided the controlling torque. These springs also serves to lead current in and out of the coil. Coming to the dust-proof case, the whole instrument is enclosed in a dust-proof case. The shape and size of this case depends upon the capacity of the instrument. Coming to the working, it works in the principle of DC motor. DC motor principle is when a current carrying conductor is placed in a magnetic field, an electrical field experiences a force, and that force is called as Lorentz force. When current passes through the coil, it produces a flux of the core. The flux density at one side increases while the other side automatically decreases. This imbalance exerts a force on the conductor in the direction of least flux density. And we discussed this point in the first video itself. So there is a cumulative flux and differentiative flux. One side there is a cumulative flux. The intensity of the flux is more on one side. The intensity of the flux is less in one side. This conductor move in the least flux density side. Let's come into the torque equation. Generally torque is nothing but force into distance. Here the force is in this direction, then the pointer is moving like this. This aluminum cylinder or moving coil rotating clockwise direction. The force is acting on this direction. So the force affecting on both sides of the coil that is perpendicular to flux density B. So F is equals to, from Lorentz force equation, F is equals to number of turns into flux density into current flowing through the coil into L, length of the conductor. So where N is number of turns of the coil, B is the flux density in the air gap, L and are the vertical and horizontal lengths of the sides of the conductor, I is the current flowing through the coil. And we know that deflecting torque is equal to force into distance, and force is NBIL into distance is D. So L and D, if you multiply these two, we'll get area of the conductor. So NBI into A. So NBA into A. Where number of conductors, flux density and area of the conductor, all these three are constants. So this deflecting torque is equals to G into I, where G is equals to NBA, which is constant. So deflecting torque is directly proportional to the current flowing through the coil. And we know that where A is the area of one turn of the coil in meter square, and G is equal to NBA, which is constant. That constant is called as deflection constant, Newton meter per ampere. Coming to the controlling torque is provided by the springs and is proportional to the angular deflection of the point. So controlling torque is proportional to the angle of deflection, that is theta, when we are using spring control. When we are using gravity control, this controlling torque is proportional to sine theta. So the controlling torque is proportional to theta for proportionally constant here K. So where K is the control constant, which is in Newton meter per degree. We know that at steady state and at final position of the pointer, this controlling torque is equals to the deflecting torque. Then Gi is equals to k theta. Automatically, T torque is equals to G by k into I, which is final steady deflection. So deflection theta is equals to some constant into I. So deflection is proportional to current. When the current increases, deflection increases. Similarly, I is equals to some k by g into theta. So that is called as current flowing through the coil. And the conclusion, the pointer deflection is linearly proportional to I. And the second one is the PMMC scale is linear and that means equally spaced. The current changes its direction, the pointer will deflect off the scale. PMMC instrument is called as polarized instrument. Its deflection depends on the polarity of its input quantity. It cannot be used to measure AC directly, but a rectifier must be used firstly to convert AC quantity to DC quantity before applying into the instrument. When we are going to measure an AC, we are using a rectifier which is used to convert AC to DC. This DC is connected to this instrument, then we will get the output. Coming to the advantages of the PMMC type instrument, which is linear scale. The power consumed of this device is very less, which is 25 microwatt to 200 microwatt. Simple and cheap, can be constructed with very high sensitivity, especially if third band suspension is used. Disadvantages of the PMMC type instrument. The PMMC instruments are only used for the direct current. External magnetic fields badly affect its operation. This can be avoided by using core magnetic type PMMC construction. That is one of the disadvantages. And not very sensitive. To have sensitivity device, a third band suspension must be used, which is expensive. So when compared to other, which is little expensive because of that. So errors in PMMC instrument. In PMMC instruments, the error occurs because of the aging and the temperature effects of the instrument. So the magnet, spring and the moving coil are the main parts of the instrument which causes the error. The different types of errors are in the instrument, which is first one is magnets. The heat and vibration reduce the lifespan of the permanent magnet. That's the first one. This treatment also reduces the magnetism of the magnet. The magnetism is the property of the attraction or repulsion of the magnet. The weakness of the magnet decreases the deflection of the coil. Coming to the second one, springs. The weakness of the spring increases the deflection of the moving coil between the permanent magnets. So, even for the small value of current, the coil shows large value. The spring gets weakened because of the effect of the temperature. So 1 degree rise in temperature reduces the 0.004% life of the spring. So we have to maintain the temperature because of that. Coming to the moving coil, the error exists in the coil when their range is extended from the given limits by the use of this shunt. The error occurs because of the changes of the coil resistance on the shunt resistance. This happens because the coil is made up of copper wire which has high shunt resistance and the shunt wire made up of a manganese has low resistance. So manganese has low resistance. So to overcome from this error, the swamping resistance is placed in series with the moving coil. The resistor which have low temperature coefficient is known as swamping resistance. The swamping resistance decreases the effect of the temperature on the moving coil. So let's see an example. Take one problem here. A PMMC instrument with 100 turns coil has a magnetic flux density in its air gap of D is equals to 0.2 Tesla. The coil dimensions are D is equals to 1 centimeters and length is equal to 1.5 centimeters. Calculate the torque, which is deflecting torque, on the coil for a current of 1 milliampere and its deflection constant deflection, which is called as deflection constant. If the device constant K is equals to 12 into 10 to the power of 3 degree per amperes. Find the spring control constant. Find the angle of deflection for the input currents 1, 2, 4 and 8 milliamperes. Conclude your results. Let's see. We know that deflecting torque is equals to NBA into I, where N is equal to number of turns, B is equals to flux density, which is 0.2 Tesla, 100 turns, and the dimension 1 centimeter into 1.5 centimeters, which is the area of the coil. So we know that deflecting torque is equal to NBIL into D. So 100 turns into 0.2 Tesla into current pole 1 milliampere, that is 1 into 10 to the power of minus 3 amperes, into length 5 into 10 to the power of minus 2 meters. D is equals to 1 into 10 to the power of minus 2 meters. So finally we got 3 into 10 to the power of minus 6 Newton meter. That is your deflecting torque. We know that deflecting torque is equals to some G into I. So G is equals to deflecting torque by I. So deflecting torque is 3 into 10 to the power of minus 6 Newton meter. By I we know that 1 into 10 to the power of minus 3 ampere. Finally, we got this value. So we know that theta is equals to G by K into I. G by K is equals to 3 into 10 to the power of minus 3 Newton meter per ampere by K is equals to, which is already given, that is 12 into 10 to the power of minus 3 degree per ampere. So that constant, total constant, we got 12 into 10 to the power of 3. And for 1 milliampere, this deflection is this constant 12 into 10 to the power of 3 into 1 into 10 to the power of minus 2 will get 12 degrees. This current is now 2 milliamperes, then it is 24 degrees. The current is 4 milliamperes, will get 48 degrees. The current is 8 milliamperes, will get 96 degrees. If you observe here, if it is doubled, the deflection is also doubled. If it is 4 to 8, it is 48 to 96. So final conclusion is, the current is doubled, the angle of deflection is doubled. That's why permanent magnet moving coil has linear scale. Thank you.